them later on. To have fun with this? I trust you recognize that this was simply an attempt on my part to get you to put to use all the stuff we presented regarding analysis of Bronsted-Lowry acid-base systems. If my analysis is correct, you could tackle this with or without charge balance support. I'm writing up the key. I had intended to have the key ready yesterday, but I'm afraid this weekend a bug bit me, so I'm a little under the weather, not entirely up to par. So I haven't got the key quite ready yet. I hope by no later than tomorrow I will have it ready, and as soon as it's ready it will of course be posted. If you tackle this with charge balance support or without charge balance support, based on correct chemistry, I'll credit either. I'm happy with either. We will of course see what you've done. QZ2 keys posted, and as I'm sure you all know and are at the same time extremely thrilled by, exam 2 this Friday. An absolutely exhilarating experience. Now then, on with chapter 19. In the main, with the exception of the salt effect, what you will see regarding our remaining considerations for chapter 19, other than Lewis acid, Lewis base stuff, which we will deal with at the very tail end of chapter 19, we are going to be showing you how Bronsted-Lowry acid-base chemistry relates to semi-soluble salt equilibria. So with that, after having recognized how to get the solubility calculated correctly for a material like calcium carbonate, in addition to KSP, you have to pay attention to KB carbonate ion. We now proceed to dealing with the solubility of, again, calcium carbonate in a water solution, now buffered at pH 8, which we established foundation for last time. Since on saturating calcium carbonate in DIW, we get a saturated solution pH of 10.0 to 1 sig fig. Since this solution is 100 times more acidic than pH 10, and since the way to kill bases is to make the system acidic, before you do any arithmetic on this system, you should start by knowing the calcium carbonate has got to be more soluble in this system. That gets you on track with the right chemistry. That's where it's all at. There's the equilibrium reaction we choose to use. Now, take a look at this equilibrium reaction. I think you recognize at a glance that if we write out the KSP equilibrium reaction for calcium carbonate and the KB carbonate equilibrium reaction and add them together, that's what we get. Right? Calcium carbonate, double arrows, calcium ion plus carbonate ion plus water, double arrows, bicarb ion and hydroxide ion. If you add those two up, that's what you get. And you played this adding reactions game earlier on in chapter 19. Really, that's part and parcel of calculating K for a complex equilibria, where you recognize what fundamental equilibria of which the complex equilibria is composed. You did some of that in 2045 too. Remember doing that? Remember Hess's law and its use? If you know delta H for reaction A and delta H for reaction B, and you add up reaction A to reaction B and get a new reaction, call it reaction C, then delta H for reaction C is delta HA plus delta HB. That's Hess's law. You did that in 2045. Now, the problem with 2045 and that approach is you only applied it to combining delta H's. All the standard thermodynamic properties of chemical systems are combinable by Hess's law. Delta S reaction, delta S reaction, delta S reaction. Did you talk at all about delta S for a reaction in 2045? What's delta S? Change in? Because I know you were asked to talk about this in 45L. You know, I'm not going to stand around waiting for the 45 lecture to catch up. But again, the 45L suffers from a serious problem. You're working in teams of 3. So I can't make anybody individually responsible for learning what's going on. Now I could solve that. I could make all 45L grades depend strictly and exclusively on exams, where you would take the exam individually. No credit at all for being in lab. Would that be fair? I think that would be horribly unfair, because it's a lab course. It's not your fault you're crammed in there in packs of 3. So we'll do the best we can with what we got. But at the minimum, I have to plead with you to pay attention to the information in the lab manual. Because when we played this game, which we will show you in detail in the next chapter, on more fundamental looks at thermodynamics, all we're doing so far is chemical thermodynamics. And the equilibrium constant for reaction is directly related to its change in free energy. That's what you want to know about a reaction. Because what you want to know about a reaction is if it can go or cannot go under the conditions at which it is being studied. And in order to answer that question, you have to assess delta G for the reaction, not just delta H. Now, I don't know what the textbook's doing, which is the delta H only. That makes no sense. Because you're shortcoming all sorts of reactions which go, but which are prohibited by delta H. Well then, why does it go? Because of the change in entropy. Being magnitude-wise outweighing the change in enthalpy. But in any case, more on that in coming chapter. Question. After recognizing that this is a combo of KSP calcium carbonate reaction added to KB carbonate reaction, is this reaction stoichiometric, yes or no? You know what the question means? You did stoichiometric considerations in 2045. I should think extensively. What does it mean to say a reaction is stoichiometric? Well, let's take a look at this reaction. Because the stoichiometric implication of this reaction is that, independent of pH, if a mole of calcium carbonate reacts with a mole of water, into solution you will put 1 mole of calcium ion, 1 mole of hydroxide ion, 1 mole of hydrogen carbonate ion, 1 mole of hydroxide ion. Now we know that if, for example, we have a liter of water as our intended solvent system, and we treat it with a mole of calcium carbonate, because I can make any mix I want in the lab, how much of the calcium carbonate will dissolve? Will this much dissolve? Is this not the molar solubility of calcium carbonate in deionized water? Yeah, this is how much dissolves. 1.4 times 10 to minus 4 moles. I can write anything on the board. I can write any equation I want on the board. You think that's a guarantee that reaction goes? I hope you learned that in 2045. An equation for a reaction is nothing but a recipe. It does not tell you at all what happens. It's an if-then clause. It's not a guarantee. That reaction as it stands, does that tell you that if I mix a mole of calcium carbonate with a liter of water, only 1.4 times 10 to minus 4 moles of the calcium carbonate dissolves? That doesn't tell you that. Now let's proceed by knowing that 1.4 times 10 to minus 4 moles of the calcium carbonate per liter of resulting system dissolves. If this reaction is stoichiometric, I will then observe a calcium ion concentration in the saturated solution of 1.4 times 10 to minus 4 molar. That's correct. But does this reaction guarantee that? In that system, never mind the buffered, never mind the pH. Will a hydrogen carbonate ion be 1.4 times 10 to minus 4 molar? When I take the calcium carbonate, mix it with water, 1.4 times 10 to minus 4 moles of calcium carbonate dissolved. That we know. Will that give me a hydrogen carbonate ion molarity 1.4 times 10 to minus 4? Will it give me a hydroxide ion molarity 1.4 times 10 to minus 4? No and no. So that's not stoichiometric. Because the part of the puzzle that's not revealed to you by this non-stoichiometric reaction is there will be carbonate ion also in solution. Because you remember in the deionized water mixture with calcium carbonate, about 70% of the carbonate converted to bicarbon hydroxide ion? That's how we got the pH of 10. Well, then 30% of the carbonate ion swimming around as is. That reaction doesn't show you that. Doesn't show you the carbonate ion, which is still in the system. So you got to be careful about these reactions. What I'm trying to do is appeal to you to learn how to interpret these reaction statements. They're not guarantees. They're not insurance policies. They're recipes. Now then, back to this specific case, where the system buffered at pH 8, for which the hydroxide ion molarity of 2 sig figs is this. Since the calcium ion on being placed in solution doesn't do anything further, the solubility of calcium carbonate is the same as the equilibrium molarity of calcium ion. But what about the equilibrium molarity of hydrogen carbonate ion? In straight deionized water, the equilibrium molarity of hydrogen carbonate ion, as well as the hydroxide ion molarity, will be 70% of this. That gives you the pH 10. Okay? But in this system at pH 8, where this value is fixed, the hydroxide ion molarity is fixed because the system is buffered. Will the hydrogen carbonate ion molarity be 70% of the calcium carbonate which goes in the solution? And 30% of the carbonate ion is still swimming around? Did we not realize this system is 100 times more acidic? And 100 times more acidic system more effectively kills carbonate ion, doesn't it? Does it not? Because carbonate ion is surely the strongest base that's put into the system by mixing calcium carbonate with water. I mean, what are you going to choose between? Carbonate ion and water? Carbonate ion is a heck of a lot stronger base. So the $64 question to wrestle with regarding this system is, how the heck does the molarity of hydrogen carbonate ion relate to S? Because as things stand, we want to get the solubility. That's the calcium ion molarity. And in order to do that, I also need to know the molarity of this. So far, the only part of this puzzle I know is the hydroxide ion molarity, which is fixed by the buffer. So as things stand, I got two unknowns and one equation. I got a problem. But based on equilibrium analysis, specifically Bronsted Lowry acid-base equilibrium analysis, can we succeed in determining how the hydrogen carbonate ion molarity in this system relates to the other possible forms of carbonate-containing things? Absolutely. What are the other possible forms of carbonate-containing things? Because now what I'm poking you about is, do you recognize at a glance how material balance applies to hydrogen carbonate ion? How does it come? How does it relate? Maybe I didn't say this back in chapter 18, although it's stated in the notes. From an acid-base standpoint, Bronsted-Lowry acid-base standpoint, material balance depends on all the viable forms of a species. What does viable mean? What does it mean? If I say viable, you don't know what it means, then you can't know what I'm talking about. What does viable mean? Possible. Can exist. Okay? All the possible forms of carbonate-containing things which can exist in a water solution as a function of H plus exchange, pH, are, if I start with hydrogen carbonate ion, then hydrogen carbonate ion can lose H plus and become carbonate ion, or hydrogen carbonate ion can gain H plus and become hydrated CO2. Those are all the possible forms. So I know from a material balance standpoint for this system that S, which we already have recognized as the calcium ion molarity, is also the sum of these three terms. Because all these terms taken together represent complete material balance for carbonate-containing things in this system. Okay? Now, are all of these forms exhibiting a concentration that has to be considered at pH 8? Or perhaps just two of the forms, or maybe just one only? Let's take a look. Well, in order to take a look, we rely on our knowledge of Bronsted-Lowry acid-base chemistry and look at the equilibrium reactions which interrelate these possible forms of carbonate-containing things to each other as a function of pH. Now, to relate hydrogen carbonate to carbonate, what are the equilibrium reactions I can use? On the board, I have used Ka hydrogen carbonate. Right? Ka hydrogen carbonate plus water, double arrows, hydronium ion, and carbonate ion. So there's an equilibrium reaction which contains hydrogen carbonate ion reactant, carbonate ion product. So the molarities of those two forms of carbonate-containing things are relatable from that relationship. Is there a different K I could also use? Kb carbonate will do the same thing. Wouldn't change anything arithmetically. Now then, if I want to relate hydrogen carbonate molarity at equilibrium as a function of pH to hydrated CO2, what can I use? Can I use Ka for hydrated CO2? Can I use Ka for hydrated CO2? Because hydrated CO2 reacts with water, makes hydronium ion and hydrogen carbonate ion. Of course I can use that. Now what have I used? I've used Kb for hydrogen carbonate ion. I've used Kb for hydrogen carbonate ion because I've written a reaction equation which has got hydrogen carbonate ion in it, so I want to know straight away how the hydrogen carbonate ion molarity at equilibrium relates to these other forms. But if you use Ka for hydrated CO2, you get exactly the same arithmetic result. Here's the new value. Here's a new value. These values are different from what you see in the notes. The values you see in the notes are close to these numbers. So don't be put off track by the slight difference in numbers, okay? Well, now, from this, we have recognized that at equilibrium at pH 8, the bicarb concentration divided by the carbonate concentration is equal to the hydronium ion concentration divided by Ka. And that's about 210 to 1. So that's showing us at pH 8, do we have to pay much attention to this? Heck no. Molarity of this is over 200 times bigger. All right? Now let's play the same game to get a concentration ratio at pH 8 of bicarb molarity to hydrated CO2 molarity. This gives us hydroxide molarity divided by Kb. There's the numbers. That's about 45 to 1. So what have I established? I've established that at pH 8, of all these possible forms of carbonate ion, only one of them has a meaningful concentration. Which one is it? Bicarb ion. Done. So guess what? At pH 8, I can say that calcium ion is equal, calcium ion molarity is S, and so is bicarb ion. Because what I've established is that when carbonate hydrolyzes at pH 8, which of course it does, it converts to bicarb ion, and that's about the end of it. No conversion to speak of to hydrated CO2 at pH 8. Not surprising. pH 8 is a mildly basic system, and this is an acid. Okay? So, based on this, I have my equation here. This has now been replaceable by S. Real tough now. Solve it for S. I get 1.1 times 10 to the minus 3 molar, which we see at a glance is bigger than 1.4 times 10 to the minus 4 molar. This is about 8 times bigger. And that's what we knew before we did any arithmetic. This system is more acidic, so it's got to be a better dissolver of calcium carbonate. Put another way, that means the calcium carbonate molarity at equilibrium has got to be greater than the observed solubility at pH 10. And it is. Now then, in a few minutes, we're going to examine this very same system with one change. We're going to buffer the solution at pH 6. See? What happens to S and bicarb molarity if the solution is buffered at pH 6? What's going to happen? Number one, will the calcium carbonate be even more soluble? Of course. Now we up the acidity of the system by another factor of 100. Okay? So more soluble even. Now, if the carbonate ion molarity has now been found to be essentially meaningless at pH 8, is the carbonate ion molarity going to have any significance at pH 6? If the carbonate ion molarity doesn't mean anything at pH 8, that's what we just showed, because the bicarb molarity is 210 times bigger than the carbonate molarity. What's going to happen to this ratio? Bicarb to carbonate ion at pH 6. Will this ratio increase? What will it increase to at pH 6? We got this on the board, let's use it right now. What does this ratio become at pH 6? Tell me. 21,000 to 1. Do you see that? Because all that's happening is the hydronium ion molarity is going from 1.0 times 10 to the minus 8 to 1.0 times 10 to the minus 6. So we multiplied the ratio by 100. That's it. Let the numbers talk to you. 21,000 to 1. Hey, we already know. If at pH 8 carbonate ion molarity means nothing, if you make the system more acidic, it's guaranteed carbonate ion molarity is not going to mean anything. Because it's the strongest base in the pot of the carbonate containing things in the system, possible carbonate containing things. Ha ha! But let's go back to this. Here is the bicarb to hydrated CO2 ratio at pH 8. What happens to this ratio at pH 6? Put another way, at pH 6, what is the predominant form of carbonate containing stuff? What is it? That's it, hydrated CO2. And not surprising, we're making the system more acidic. The more acidic you make the system, the more you're going to protonate the protonatable bases in the system, which means bicarb ion in this case. Look at the numbers. Okay. This becomes 1.0 times 10 to the minus 8. And this becomes 0.45 to 1 at pH 6. The predominant form of carbonate-containing stuff in the pot at pH 6 is this stuff. So, will we have to modify our arithmetic to calculate the solubility of calcium carbonate at pH 6? Yeah, because what we're finding out is that the bicarb molarity at pH 6 is hardly equal to S. It's a lot smaller than S. Keep that in mind. We proceed. Subtopic C for the various topics listed in Chem Notes. Chapter 19, salt effect. On the board I have written that the first thing you did in chapter 19 was to get at the solubility of materials like silver chloride, where the solubility is correctly calculated strictly from KSP. Because there's no hydrolysis, there's no acid-base chemistry with which to be concerned. So the square root of KSP for this stuff gives you the solubility. There's the KSP, there's the solubility. All right? Now let's get at the salt effect. I repeat, each and every ionic compound is a salt. Salt's just a generic term for ionic compound. A lot of students think salt, that means exclusively sodium chloride. Nope. Every ionic compound's a salt. Like sodium hydroxide, a salt. A hydroxide salt, a basic salt. But as I said, I advise you strongly, do not season your hamburger with sodium hydroxide. Now, if you do that, I guarantee you won't have any residual bacteria living in your mouth. That'll do a hell of a lot better job cleaning this cavity called the mouth than toothpaste. But if you do that, you probably won't have any tongue remaining either. And I'm sure you'll have to see a doctor quickly to get all these blisters fixed that will have developed inside your mouth. So don't do that. You know, or if you want to do that, at least let me know so I can first contact my attorney. Because I don't want to be charged in court by a student who said, my chemistry teacher told me to put sodium hydroxide on my hamburger and I did it and look what happened. Ah. Let's take silver chloride, the very same stuff where hydrolysis, acid-base chemistry means nothing, and dissolve it in 1 molar sodium nitrate solution to get at the salt effect. Or consider dissolving it in 1 molar sodium nitrate solution. Question number 1. If I saturate 1 molar sodium nitrate solution with silver chloride, will I get this solubility for silver chloride? Will I get a solubility for silver chloride that's smaller than this number, or will I get a solubility for silver chloride that's bigger than this number? It's got to be one of these three, and I have a feeling right off the bat, since this is a special topic, you will not say the solubility is 1.3 times 10 to the minus 5. So just for fun, I'll ask for this vote. How many vote that if I attempt to dissolve silver chloride in 1 molar sodium nitrate solution rather than straight deionized water, I will wind up with a silver chloride solubility that's smaller than 1.3 times 10 to the minus 5. Now I'm going to look for those who don't vote. Because if you don't vote, I'm going to go to every one of these special quizzes, and for the non-voters, I'm going to write minus 1 million at the top. Now, how in the hell you're going to earn that back is beyond me. Okay? Either that or pay $1,000 toward our beer and pizza party. Okay? Cash on demand. Or you can leave me your credit card. Along with your driver's license. because I want to be sure your credit card's valid. All right. How many vote that the silver chloride solubility will be bigger than 1.3 times 10 to the minus? Wonderful. From that, I infer that you've paid attention to the information on the salt effect that's in the notes. Either that or you're one hell of a bunch of lucky guessers. I'll take the first choice. That you're doing what I asked you to do as students so that you learn as expeditiously and efficiently as possible. What's going on here? Well, from a rigorous chemistry terminology standpoint, what's going on here is that the activities of silver ion and chloride ion are enhanced substantially when I take silver chloride and try to dissolve it in a system where I have got a high concentration of ions, right? 1 molar sodium ion, 1 molar nitrate ion, very high concentration of ions, none of which react with the components of the salt whose solubility is under consideration. You recognize at a glance that this system, PSI, sodium ion, nitrate ion, okay? In this system, the sodium ion react with chloride ion? Absolutely not. Sodium chloride's daggone soluble. So I tell you, that's why these textbooks write in NaClAQ. That's wrong. That's stupid. It doesn't mean anything. And it even suggests that the ionic compound is molecular. What is this junk? That's hard. Nitrate ion. Is that going to react with silver ion? Have you not recognized that nitrate ion, for example, from your work in 46L, is a stuff which forms very soluble materials, very soluble ionic compounds. So you can't succeed in testing for the presence of nitrate ion in solution by precipitation because its salts are soluble. So you got to do that fancy test of getting nitrate ion to A, be reduced, and B, be complexed, to give you that brown color that forms in solution on top of the ferrous ammonium sulfate crystal. Right. That's what you're doing in the lab to test for nitrate ion. Point: neither sodium ion nor nitrate ion, which are each present in great abundance in this solution relative to silver ion and chloride ion, react chemically with silver ion or chloride ion. So why the heck is the solubility of silver chloride going up? Well, again, the rigorously speaking answer is here. In the main, what this amounts to is, in this solution, sodium nitrate solution, silver ions and chloride ions can behave far more independently of each other than they can in the deionized water system. Well, if they can behave far more independently of each other, then you can put a whole lot more of them in solution. That's why the solubility goes up. Why do they have this ability to behave far more independently of each other in this solution? Well, back to Coulomb. Imagine that for this system, you're a silver ion. You look like a silver ion right now. Tell me, what will be attracted to this silver ion in this solution? Nitrate ions, right? They're oppositely charged. Okay? So nitrate, 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 nitrate. I'm getting tired of nitrates here. All around the thing. Front, back, all the way around. Okay? But these nitrate ions, are they going to swim toward the silver ion all by themselves? Will the nitrate ions successfully swim away from the sodium ions? Heck no! Sodium ions are attracted to the nitrate ions just like the silver ions. So what you're doing is you're going to wrap an ionic sheath, a large ionic sheath, or sheath of ions if you prefer, around this silver ion. Same for chloride ion. First the sodium ions are attracted because they're oppositely charged, and the sodium ions will drag with them the nitrate ions. Okay? So what you got now is a system in which a silver ion in solution is in this protective sheath of nitrate ions and sodium ions. A chloride ion in the system is in this protective sheath of sodium ions and nitrate ions. Well, this protective sheath keeps the silver ions and the chloride ions from getting together. Because the only way I can make silver chloride is for silver ion and chloride ion to touch each other. Well, now it's a hell of a lot more difficult for them to touch each other. Their activities have gone up. Their abilities to behave independently of each other have increased substantially. Upshot, solubility silver chloride has gone up substantially. Now, there's no simple way to get at the arithmetic for calculation of a salt solubility, a semi-soluble salt solubility like silver chloride. At least none that I know of. You can do it as a function of concentration. There's data available, but I'm not going to bother with that. Okay? So let it be said, silver ion insulated far more effectively than it is in straight water. Chloride insulated far more effectively than it is in straight water in the sodium nitrate solution. Prevents silver ion and chloride ion from getting together, reacting, and making silver chloride. Net upshot, solubility goes up. Statement: on any remaining quizzes or exams, I'm not going to ask you about the salt effect. I just wanted to make mention of it because it is part and parcel of semi-soluble salt considerations. So let's get on with... Did you hear what I said? No quiz or exam questions on salt effect. Does that make it sharp and clear? Because I know what I do. Since we don't have calculations, I see you drawing all these pictures of this. Look like a bunch of BB shot splattered over a piece of paper. I don't want to see that. Hurts my eyes. And I don't want you wasting all that valuable graphite or ink. So we go on to section D, which is just another type of chemistry related to semi-soluble salts. Chemistry which you have in fact been doing in the lab since assignment number 2. Offering the possibility for an ion in solution to have its presence detected by giving that ion the opportunity to react with another ion that you add to the solution and form a precipitate. Assignment 3, 46L, which by now you should all be through, for those of you who are in lab. You investigated in assignment 3, 46L. The solubilities of 4 calcium salts. Count them. Remember what they are? Calcium chloride, calcium hydroxide, calcium carbonate, calcium sulfate. I stated those salts in that order because that's the order in which you studied them with your work in 46L. What chance do you have of precipitating calcium ion as the chloride? Come on, you've been in the lab doing the work. What chance do you have of precipitating calcium ion as the chloride? I'm listening. None. Why not? Isn't that the solution you use for calcium ion in the lab? I mean, if I'm in there in the lab dealing with half-molar calcium chloride solution, half-molar, does that sound like calcium chloride's pretty damn soluble stuff? Yeah, good. Now then, after that, this is 46L assignment 3. You investigated reaction of calcium ion with hydroxide ion. Then you investigated reaction of calcium ion with carbonate ion, and finally calcium ion with sulfate ion. Okay? For these 3 salts, each of which offer a method of testing for calcium ion by precipitation. If you have a water solution, and you know nothing about the pH for this water solution, And you also know that the solution is rich in sodium ion because you've subjected it to flame test analysis. That means if you want to find out if calcium ion is or is not in that solution, can you use reliably flame test analysis? No, why not? Because the sodium ion flame is far more intense than the calcium ion flame. And all you see is the sodium ion flame. So calcium ion is still hiding from you if it's in the solution. So you have now to make a decision. The decision being, I will now be forced to test for the presence or absence of calcium ion by precipitation. And if so, which salt shall I try to form? Which of these calcium ion salts is easiest to form in deionized water solution? Calcium carbonate. Because it is calcium hydroxide, calcium carbonate, calcium sulfate. Calcium carbonate is easiest to form because of these three salts, it is the salt which shows the what? What does it show? It shows the lowest water solubility of these three. So it's easiest to precipitate deionized water. Okay? But what if you got a solution that's distinctly acidic? Is calcium carbonate readily precipitatable from a solution that's distinctly acidic? What have we been doing with these analyses? Showing you that as you make the solution progressively more acidic, calcium carbonate solubility increases. So if you got a system that's distinctly acidic, forming calcium carbonate is not easy. But of the salts that I mentioned, is one of these still readily formable in a distinctly acidic solution? If so, which one? Calcium hydroxide? Want to form that readily in a distinctly acidic solution? Well, it must be calcium sulfate. Any of you remember how you prepared calcium sulfate in the laboratory? What was the recipe? Well, you used calcium chloride solution because that's your calcium ion source. What was your sulfate ion source? You did this. Nobody remembers? 3 molar sulfuric acid solution. 3 molar sulfuric acid, a distinctly acidic solution. It's got a pH lower than 0. Yet in that system, calcium sulfate formed readily. So you now know. If I got a distinctly acidic system, I can still readily precipitate calcium sulfate. But forget calcium carbonate and calcium hydroxide. In any case, the first consideration with respect to this subtopic is simple arithmetic. If I have a solution that's 10th molar in sulfate ion, what is the solubility of gypsum? What is the solubility of gypsum if I don't have if I just have deionized water? So we got 2 questions. Solubility of gypsum in deionized water versus solubility of gypsum in a solution which is 10th molar in sulfate ion. Well, there's the KSP. And for this system, need I pay attention to sulfate ion base strength? Sulfate ion hydrolysis? Or can I get an acceptable value for calcium sulfate solubility in straight water if I just take the square root of that number? Does that give me an acceptable value for calcium sulfate solubility? The square root of that number. Does that give me an acceptable value? Well, if you think it doesn't give me an acceptable value, then you're arguing that the sulfate ion hydrolysis must be considered. And in a moment, we're going to demonstrate that sulfate ion hydrolysis means nothing until you reduce the pH to values on the order of 2 or lower. statement thereafter. The square root of that number is calcium sulfate solubility in straight water. Now what's the solubility of calcium sulfate in my 10th molar sodium sulfate solution? Aha! Now, this is still S. Because I'm looking at calcium sulfate. I'm going to leave out the waters just for speed. Establishes this equilibrium. I've not put any external source of calcium ion in the pot, so the calcium ion molarity is the same as the calcium sulfate molarity in the saturated solution. And in straight deionized water, this is also S. Aha, but now I got 10th molar sulfate ion. So this is 0.10 plus S. So my arithmetic would be this. Now in calculating S, can I see at a glance that the S value has got to be a lot smaller than the square root of this number? And the square root of this number is 3.0 times 10 to the minus 3. Well, if S is a number that's a lot smaller than 3.0 times 10 to the minus 3, when I add S to 0.10, am I going to change 0.10? Nope, not at all. So the solubility for calcium sulfate in 10th molar sodium sulfate solution, okay, is this. Nothing fancy about this. Now what's this number mean? This number means that if I have 10th molar sulfate ion as my precipitating system, like that, okay, I can find calcium ion by precipitation as calcium sulfate at any calcium ion molarity which is bigger than this number. That's what this means. Any calcium ion molarity bigger than this number will give me a Q value which is bigger than K. So precipitate can form. No guarantee, but at least now I have a chance to make the precipitate. Okay? You play the same game with calcium hydroxide. It's not hard. What about sodium carbonate? 10th molar. For starters, if I have this solution on the side shelf and I want to see about precipitating calcium ion, can I expect this solution to be a whole lot better calcium ion detector than this solution? Can I expect this solution to be able to find calcium ion at a molarity which is a lot smaller than this number? Well, let's look at the arithmetic. 6.2 times 10 to the minus 9. There's KSP. This again will be S. And if I take the carbonate ion molarity to be 0.10, then this will be 0.10 plus S, the carbonate ion molarity, and S will be this divided by 0.10. 6.2 times 10 to the minus 8. And 6.2 times 10 to the minus 8 is a heck of a lot smaller than this. So this goes back to what we said at the start of this conversation. I can well expect that I have a much better chance to find calcium ion in a water solution, if it's there, by carbonate precipitation compared to sulfate or hydroxide precipitation. Okay? Now, notice what I wrote over here at the 10th molar sodium carbonate solution. I wrote, be careful. Why do you think I wrote this? All right, let me be more direct. Do you think in a bottle on a side shelf which bears this label that the carbonate ion molarity is 0.10? How would you find the carbonate ion molarity? We got to go back to chapter 18. Will you write Kb carbonate? Which is 2.1 times 10 to the minus 4 equals bicarb molarity times hydroxide ion molarity divided by the equilibrium molarity of carbonate ion. So you'll have x squared over 0.10 minus x, won't you? So will you find the true molarity of carbonate ion in a bottle on the side shelf which has this label? Right? This is the label on the bottle. In this solution, will the carbonate ion molarity be 0.10 or a smaller value? Smaller. A lot smaller? No. It'll be about 0.09 something or other. But in any case, if I establish carbonate ion molarity to be 0.10 in a solution, which means I need sodium carbonate solution to be about 0.11 molar as I made it. Okay. We've shown here, I mean, even if the carbonate ion molarity was 0.09, I'm still going to find calcium ion a whole lot more readily and easily because of the far lower solubility of calcium carbonate compared to the other materials here. Again, this is plug-in arithmetic. This is nothing. Now then, let's go to question 1912. (1912) says, just to be sure I got the right question here. Yeah. Water solution buffered at pH 6. We spent some time over here talking about the calcium carbonate solubility at pH 6. Okay? Is gypsum, that's a mineralogist name for calcium sulfate dihydrate, or calcium carbonate? Easier to form. I think I said this before. Are you familiar with this stuff at all? Gypsum? You got any practical familiarity with gypsum? You ever had a cast on a broken bone? I hope not, but if you have, you probably had a gypsum cast, where they take plaster of Paris, which is calcium sulfate hemihydrate. That's a dot with a 0.5 water, and they add water to it. And it reacts to make gypsum. And that's your cast. Okay? And then when you get the cast off, they get a big saw, hoping they don't cut your arm and leg off with it. Okay? Okay. Any of you ever do any wall fixing at home? Plasterboard? Sheet rock? What do you want to call it? You know? That's the main ingredient in sheet rock. Interesting stuff, isn't it? Calcium sulfate dihydrate. Because you know, I'm sure I mentioned this before, but it's worth mentioning again, I believe, that under normal laboratory conditions, the principal phase exhibited by the material called water is liquid. Calcium sulfate dihydrate. Per mole of calcium sulfate, you got 2 moles of water in there. Have you ever at home observed your walls to be crying? Have you seen that? Is calcium sulfate dihydrate particularly soluble in water? When you were a little kid, did you ever go smudge the walls? Smudge the walls? And mommy comes along after you, gives you a little thwack. Don't do that! Whack! And takes a damp sponge and soap probably and goes to clean the wall, wipe off your smudge. You smudgy kid, you. Okay. Do you see the wall dissolve? Would you like to have walls at home made out of sugar? Crystalline sodium chloride. Hey, in a dry environment, crystalline sodium chloride is pretty damn stable stuff. Is it stable in the presence of water? You want your walls at home made out of sodium chloride? Got a hole in my wall. Because of the chemistry of this stuff, water liquid is turned into water solid when it's part and parcel of the composition of this stuff. Chemistry does all kinds of marvelous stuff. And we're trying to have you learn about some of this marvelous stuff. Okay? So there's the issue. Now first, the simple case, calcium sulfate. Statement. S calcium sulfate at pH 6.00 equals square root of KSP equals 3.0 times 10 to the minus 3 molar. I make that as an assertion. But a number of you a while ago were attempting to tell me that if I'm going to compute the solubility of calcium sulfate, then I have to consider sulfate ion hydrolysis. A statement with which I take serious issue. Unless the solution is substantially acidic. Now we have a system buffered at pH 6. Can we determine by simple calculation to what extent sulfate ion hydrolyzes at pH 6? There's the hydrolysis reaction. The sulfate ion, as we know, is a Bronsted base which is stronger than water. And there's the hydrolysis reaction. K is Kb sulfate, which we know how to get. So I'll just take the liberty of writing it down straight away. 8.3 times 10 to the minus 13. Hey, that's a pretty small Kb value. Good deal larger than Kb water, which accounts for why sulfate ion is a stronger base than water. But let's take a look at the impact of this K value on hydrolysis of sulfate ion at pH 6. So I'll write the equilibrium constant. Now I'm going to rearrange this equilibrium constant so that it reads as a ratio of sulfate ion over hydrogen sulfate ion. Okay? Simple algebra rearrangement, nothing fancy about this. And at pH 6, what's the hydroxide ion molarity? Would you like to divide 1.0 times 10 to the minus 8 by 8.3 times 10 to the minus 13? Well, let's gee whiz it. Instead of 8.3 times 10 to the minus 13, let's just call it 10 to the minus 12. Fair enough? Okay? This is kind of close to 10. So we'll call this 10 to the minus 12. What's 10 to the minus 8 divided by 10 to the minus 12? 10 to the fourth. A mere 10,000. And the number's bigger than 10,000. Because we whiz the denominator of what we have on the board to be 10. And it's smaller than 10. If you do the arithmetic, you'll find out it's 12,000. You find out at pH 6, the sulfate ion molarity, compared to its hydrolysis product molarity, which is hydrogen sulfate ion, is 12,000 to 1. So am I looking at it in hydrolysis of sulfate ion that amounts to anything? Hell no. So I repeat my assertion. This is correct for solubility of calcium sulfate at this pH. Now what about calcium carbonate? Let's go back and use this stuff. Because we've already recognized at pH 6, the bicarb to H hydrated CO2 molarity is 0.45 to 1. Right? So now when I look at this reaction again, this is still what I want to know, S. Now, the bicarb molarity is nowhere near S. It's a lot smaller than S. And at pH 6, this becomes this. Okay? Well then, at pH 6, how do we relate the value for question mark, which is our algebraic representative for the bicarb molarity, to S? Let's go back to this. Okay? At pH 6, which of these terms can we immediately strike? This is out. That didn't mean anything at pH 8. Well, anything more acidic than pH 8, that clearly means nothing. Okay? Now then, let's go back to what we got here. Because of this arithmetic, that we left on the board, we see that H2CO3 molarity is equal to, this goes up there, or 0.45 H2CO3 molarity is equal to this. That okay? Nothing fancy. I got this over, this is equal to 0.45 over 1. So this molarity times 0.45 is equal to this. Okay? Now, that means that this molarity equals this. So let's go back to my S, because at this point I know that this is true. Because the carbonate's out. And I want to have one unknown up here. So I'm going to take this and replace it by this. From which I get a relationship between bicarb and S. That's all there is to it. That's all there is to it. Now when you do the arithmetic, you'll find out that up here, this becomes about, let's see, 0.33S. You do the arithmetic. Whoop. No, 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 no. S, it becomes about S over 3.3. Because we have proved that the bicarb molarity is a lot smaller than S. Okay? You can do that from what we got here. And when you work through the arithmetic, you'll get S equals, I got the value here someplace. Where have I got in this flurry of stuff? Here we go. Where are you? About 2 times 10 to the minus 2 molar. I mean, as we already knew before we did this arithmetic, at pH 6 the calcium carbonate molarity is going to be a whole lot bigger than it was at pH 8, a whole lot bigger than it was at pH 10. Well, not a whole lot bigger, but certainly bigger. Okay? So I ask now that you look at this number, because that is the calculated calcium carbonate solubility at pH 6, and this number. Because that's the calculated calcium sulfate molarity at pH 6. Which value is smaller? This one's smaller, isn't it? Well then, last question. We're back in the lab. I issue you now an unknown 5AB. Okay? You can't test for calcium ion. I flame because the sample's got sodium ion in it. And you've already done a saturated solution. You've done a solution pH analysis because your sample's soluble. It's a soluble sample, okay? Your solution pH analysis, you're doing this unknown is pH 6. And you know in a lab, the best you can do is about plus or minus a pH unit with the indicators, but it's reliable. So you get a pH about 6. You need a test for calcium ion, and you got to do it by precipitation because the sample's got sodium ion in it. Flame test is out. So you go to the side shelf, and here you see half molar sodium sulfate solution, and here you see half molar sodium carbonate solution. Which of these solutions will you use to test for the presence of calcium ion in your solution at pH 6?
Sodium sulfate.
You want to tell me? Which one? Sodium sulfate solution or sodium carbonate solution? How many vote sodium sulfate solution? I vote against every one of you. Because that damn solution you're working with in the laboratory, is it a buffer? 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 No! So as soon as you start putting carbonate ion in there, the pH is going up. And as soon as the pH goes up, calcium carbonate's a hell of a lot easier to form. Ha ha, I tricked you. This buffer, that one in lab, not buffer. Always think about the environment.